Power is a word that is in our common language, but in physics, power means something a little bit different. In physics, the definition of power is the rate at which work is done. We've seen a definition similar to this before, the rate at which something is done, or the rate at which something changes. Anytime we see an equation that has that word rate in it, that means we always have a fraction with time in the denominator. Power is a capital P, and since it's the rate at which work is done, we put work in the numerator here. Another way of saying this would be the rate at which energy changes with respect to time. Of course, when we get a new thing, we have to have new units. And so if we think about the units here based on the equation, we know that work is in joules and time is in seconds. Except we don't really call it a joule per second, we call it something else, and it's something that you should be familiar with, a unit that you've heard before. The unit of power is called a watt. And the symbol for watt is a capital W, not to be confused with the symbol for work. Now this equation gives us the average rate of which work is done, or the average power. But we can also find the instantaneous power. Remember that word instantaneous, when we had velocity or acceleration, meant at a specific point in time. So we can do that by transforming this equation a little bit in the following way. I know that work is equal to force times displacement times the cosine of theta. When I divide that by time, I notice that I have a delta x over delta t. That is otherwise known as the velocity. So another way in which I can find power is the force times the velocity times cosine theta. And again, this could give us instantaneous velocity, or instantaneous power, if we know the velocity at one specific point in time. You could also use this to find the average power if you have the average velocity. Next, we'll do some example problems using both of these two equations so we can figure out when it is best to use one or the other. In this example problem, we have a skier being pulled up a slope by a motor-driven cable, like what you would commonly see at a ski resort. The first part is actually review. We're asked to find how much work is required to pull him up at a constant speed. And then in part B, we'll insert the new concept of power to find out how much power the motor must have. So for starters, I'm going to assume that the slope looks something like this. And my skier is being pulled up this ramp. We know that this is a 30-degree angle here. To find out how much work it will take, I'm going to focus on the fact that we know that the net work is equal to the change in kinetic energy. Because it says at a constant speed, I know that the change in kinetic energy is equal to 0. When I think about the forces acting on my skier, I know that there's tension from the cable pulling him up. I know that there's gravity pulling him downward, and I know that there's normal force. We're going to assume that there's no friction in this case because the friction is really small between oiled skis and the packed snow beneath them. So we only have two forces that'll do work. Normal force does no work because it's perpendicular to the ramp, but the force of gravity does work, and the tension does work. Those two values of work added together equal 0. So that means that the work done by the tension, which is the work done by the motor-driven cable, is equal to the negative of the work done by gravity. The work done by gravity is something that we have enough information to calculate. Part A just says how much work is required, but really what they're trying to get at is how much work does the motor-driven cable do. So, work done by gravity is the force of gravity times the displacement times the cosine of theta. We know the force of gravity is mass times gravitational acceleration, so 70 kilograms times 9.8 meters per second squared, times our displacement, 60 meters. The tricky part is figuring out what is cosine of theta. I've already drawn my vector for displacement on my ramp up here, so let's add in a vector for gravity. The angle that I'm looking for is the angle between these two vectors, as shown in that marked thing right here. So I have to think about exactly what that angle is. Well, if I were to draw a line that kind of bisects that angle, I could see that this is a horizontal line and my displacement vector is parallel to my ramp. Therefore, this angle right in here has to be 30 degrees. And my horizontal line is perpendicular to my gravitational force, and so the angle between force of gravity and displacement is 30 plus 90, or 120 degrees. You, of course, need to make sure that your calculator is in degree mode as you're doing this math. But if you plug this all into a calculator, you'll find that the work that is done by tension is 2.1 times 10 to the 4th joules. Moving on to part B, we want to know how much power is required. Well, to calculate power, I have two options. I could do work divided by time, or I could do the force times the velocity. I don't have a number for force this time, and because I don't have a number for force, I'm going to focus on power being work over time. We already know the work, 2.1 times 10 to the 4th joules. We don't have a time yet, though. However, that's fairly simple to calculate. Because we have a constant speed, which means no acceleration, I'm allowed to use the equation that velocity is displacement over time. We know that displacement is 60 meters, and we know that velocity is 2 meters per second. That means that to calculate time, I do displacement over velocity, or 60 meters divided by 2 meters per second, which of course gives me 30 seconds. Therefore, the power that the motor must have to perform this task is 686 watts. Let's take a look at another problem where we need to calculate power. This second problem deals with an elevator that starts from rest and moves upward for 3 seconds, and it's accelerating as it moves upward. Part A wants to know the average power of the elevator motor during this time, which means that we're looking for the average, we're going to have to look for the work that is done by this elevator motor. And to do that, I'll start off by using the work kinetic energy theorem, which tells me that the net work is equal to the change in kinetic energy. The change in kinetic energy, we know, is the final kinetic energy minus the initial kinetic energy, or 1/2 mv final squared minus 1/2 mv initial squared. The problem tells me it starts from rest. So 1/2 mv initial squared is equal to 0. I'll work on calculating the 1/2 mv final squared in a moment. I also know that the net work is equal to the sum of the work. And in this case, we have two forces that are doing work. We have work done by the force of gravity, as well as work done by the force from the motor. So those two added together equal 1/2 m v final squared. Now, what I'm really trying to find is the work done by the motor, so that I can then calculate the power done by the motor. So, if I solve for the work done by the motor, I would have 1/2 m v final squared minus the work done by gravity. And to find the work done by gravity, 1/2 m v final squared minus the force of gravity times the displacement times the cosine of the angle between the force and the displacement. It's time to start plugging some numbers in now. So I have 1/2 times the mass, which is 650 kilograms, times the final velocity, which was given to us as 1.75 meters per second. Don't forget to square that value. Minus the force of gravity, which can be found by multiplying 650 kilograms times 9.8 meters per second squared, times the displacement, which is something that we need to calculate. I'm going to leave that blank for a moment, times the cosine of the angle between force and displacement. This problem tells me that it's moving upward. I know that gravity acts straight downward. Therefore, the angle between the force of gravity and the displacement is 180 degrees. Let's calculate that displacement for a moment. So, I know that one equation I can use is a kinematics equation, which says that delta x is equal to 1/2 v initial plus v final times time. And I know all my information to be able to calculate this. I know v initial is 0. I know v final is 1.75 meters per second squared upward, so I put it in there as positive. And I'm told the time that it takes is 3 seconds. When I multiply all of that out, I get a displacement of 2.625 meters. That's a few more sig figs than we really have, but I'm not too worried about that right now. So I'll plug that number in down here for displacement, and then plug all that into my calculator to find out how much work the force of gravity does. And when you do that, you should get 1.77 times 10 to the 4th joules of work. But this problem isn't looking for how much work, it's looking for how much power. So to finish this problem, I have to use the equation power is work divided by time. We know that work is 1.77 times 10 to the 4th joules. And we know that the time to do this is 3 seconds. So when I divide that number by 3, I end up getting 5,906 watts. So that gives me my total amount of work that is done. And that's part A. And part B says, how does this amount of power compare with its power during an upward trip with a constant speed? Let's look at this problem again, kind of starting from scratch, but I'm actually going to work on the work that I already have up here. If we were going at a constant speed, then that tells me that the net work would be equal to 0, because there would be no change in kinetic energy. So that tells me that the work done by the motor is equal to the negative of the work done by the gravitational force. We know that can be calculated by doing 650 times 9.8 times our displacement. Now it's not going to be the exact same displacement, because this displacement assumed that it started from rest and was speeding up to going 1.75 meters per second. We can assume that, or we know that the displacement depends on how fast it's going. And in part B, it doesn't tell us what that constant speed is. However, I can still think about it a bit. If that constant speed were to be less than the average speed during this trip, then it would end up being the case that the amount of power done is less than the total amount of power. And actually, typically, the amount of power done in this case, which is the work over the motor divided by time, typically ends up being smaller than the amount of power here. And that should make some sense to you if you just think about it, because it takes more force to pull something upward while it's accelerating than it does to pull it upward if it's not accelerating. So typically, again, because we don't have numbers in part B, we can't assume what speed it is traveling at. But often, the amount of power that it would take going at a constant speed would be less than the amount of power that it would take to accelerate.